Time to resume David's talk.
Okay, yeah, so first let me take any questions from the last talk, if there are any. Anyone have any? Yeah, Ravi.
Do you want to do a 2-minute overview of what the last talk, I mean?
Oh, sure, in case people were not here, yeah. Okay, so what we did is we're studying dimensionality reduction in the context of least squares regression. We introduced the notion of a subspace embedding, showing that if you have a subspace, you can reduce its dimension to something much smaller and preserve the norms of every vector in that subspace. And that was the basic primitive that we used for regression. It sort of immediately implied algorithms for regression. The question is, how do you do the dimensionality reduction? What kind of random matrices do you use? We saw that Gaussian matrices work, but they're too slow. I also mentioned the subsampled randomized Hadamard transform, which is faster and which Ken will give a proof on tomorrow. And we focused mostly on CountSketch, which was very good for sparse input matrices. And so we were in the proof of showing that CountSketch gives a subspace embedding. So in that proof we said that all it comes down to is showing an approximate matrix product with Frobenius norm error, because that upper bounds an operator norm error, and that operator norm error was enough to get a subspace embedding. So then we started looking at how can we achieve this Frobenius norm error, and we said that this is an approximate matrix product. And so we said, okay, so let's look at distributions on matrices S which satisfy what is called the JL moment property, meaning that they preserve norms of fixed vectors with good probability. And we said if they have this property, then they have this approximate matrix product property that we want. So that's what we proved last time. And so we're finally left in the proof of just showing that this CountSketch matrix does have this JL moment property. And so we started by showing it has the right expectation, it preserves norms, it's unbiased. And I'm just going to quickly mention a variance calculation, but I won't get into the detail. Yeah.
So one point is CountSketch does not give you exponentially small failure probability, so you cannot just do the union bound.
That's correct. So as I kind of hinted at, so these bounds are tight for CountSketch. So if I apply CountSketch to a D by D identity matrix, what I'm doing is I'm hashing the rows of this identity matrix into buckets, k buckets, if k is the number of rows in my CountSketch. And the problem is if two of these rows collide into the same bucket, then I only have d-1 non-zero rows in my image S times A. If I have d-1 non-zero rows, I'm not going to have rank larger than d-1, which means I can't preserve a d-dimensional subspace. So really the question is just, if I throw d balls into, how many bins do I need so that if I throw d balls into them, I'll have 1 minus delta success probability of them all getting perfectly hashed. Right? And so you sort of need at least d squared rows just for constant probability. And sort of d squared over delta is where that bound was coming for higher probability. Yeah. And so there was some complaint, well, it's a linear dependence in delta, how can you do better? Some of these other works I alluded to were instead of choosing a single non-zero entry per column, if you choose like 100 non-zero entries per column, or log d number of non-zero entries per column, they achieve not only a better dependence on d, so instead of d squared you get like d to the 1.1, but they also achieve a better dependence on delta. Yeah. So that's the summary. Any other questions? Okay, Marco, or no? Okay. So one other question that came up was, we're getting a polynomial dependence in epsilon. So the time is proportional to is polynomial in d over epsilon. And for some of the statistics people in the audience, this is totally not acceptable. You'd like epsilon to be very small. So one thing we'll see in this talk is how to use sketching as a preconditioner for gradient descent, for which you can get a logarithmic dependence on 1 over epsilon. And therefore you can set epsilon be really small, like 1 over square root n, if n is your number of examples. And this will be more suited for those applications. Okay, if there are no other questions, then I'll just continue. Okay, so so we showed that if we choose a CountSketch matrix S, then the expected value of the squared norm of Sx is the squared norm of x. It was unbiased. Now, what we needed to show was this JL moment property. So we want to show the JL moment property here with L equals 2. So we really need to compute the expectation of the squared norm of Sx minus 1 squared. Okay. Now I can expand that square, and I'll get the expectation of the 4th power of the norm of Sx, minus twice the squared norm of Sx, which I've already computed the expectation for, plus 1. So really this comes down to understanding what is the expectation of the 4th power of the norm of S times x. Okay, that's all we need to compute. And so it's a mess. Okay, I'm not going to do it in the talk just to keep things simple. But really, it's very simple. Okay, so all you do is so this is the expectation of the 4th power of the norm of Sx. So this is the squared norm of Sx squared. So I have sort of 2 copies of what I had before. I have a sum over the k coordinates summing over j, and I also have the sum over k coordinates summing over j prime, and I have both of those expressions that I had before. And really all this is a second moment calculation. I mean, so you can write out the whole thing. I don't expect you to parse this on the fly, but what it comes down to is you again have these random signs inside of each of the expectations. And if you remember, for the expectation calculation, we said that if I look at sigma I1 times sigma I2, and I1 is not equal to I2, then that expectation is 0. And so now it's a little bit more complicated. I have an expectation of sigma I1 times sigma I2 times sigma I3 times sigma I4. When is that expectation non-zero? So I have to be able to group these indices into pairs to get a non-zero expectation. So for instance, they could all be equal to each other. And then I'll get some expression here that I can calculate. Or maybe these two are equal and these two are equal, but they're not equal to each other. So I just go through each of the cases, and I bound this expression. It's not very interesting. It's very straightforward. So you do it. There's some slides. The math is here just for archival purposes. But at the end of the day, what you get is that the expected value of the 4th power of the norm of Sx is between 1 and 1 plus order 1 over k, where k is the number of rows in your CountSketch. Okay? That's what you get. And so, now we want to show that CountSketch has this JL moment property. So we wanted to, for the value L, the moment equaling 2, so we have to look at the expectation of the squared value of the squared norm of Sx minus 1. And, just expanding it, we plug in 1 plus 2 over k for the expected value of the 4th power of the norm of Sx. And then we have minus 2, because it's minus twice the expectation of the squared norm of Sx, plus 1 for that 1. And we get 2 over k. And if we just set the number of rows k in our CountSketch to be 2 divided by epsilon squared delta, then this quantity is exactly what we want for the JL moment property. Okay. So that's all the proof does. Any questions about that? Again, it's just a calculation. Yeah, Robbie.
Could you not do higher moments too, or it's not accurate enough?
So CountSketch, this is already tight. But again, looking at higher values of L is useful for some other works. So one work is by Bourgain, Dirksen, and Nelson, where they show that if all the leverage scores of your matrix A are small, then you can get better bounds. So just you can get D rows instead of D squared rows. One thing they look at is higher moments, for example. And the works that look at the trade-offs, number of non-zeros per column, instead of being 1, if I have like 100 non-zeros per column, you can look at higher moments and get better bounds. Yeah. But for us, L equals 2 is enough. Yeah, Fred.
How about this dependence on 1 over epsilon, the linear dependence?
Yeah, so that's a great question. So we're going to see how to do a log 1 over epsilon dependence. Yeah, okay. Okay, so just to wrap up, so this was the JL property. We showed CountSketch satisfied it. We also showed a transition statement. If you have the JL property, then you have approximate matrix product. And if you remember, that's all we needed for the proof. So we showed L equals 2 and 2 over epsilon squared delta rows suffice. We wanted a matrix product result of this form, which is a little bit different form than the form that's proven here, but it's really the same thing. Okay, so if I if I set epsilon squared equals 2 over k delta and plug it in here, then I get 6 over delta number of rows k, and I just make this delta. This is 1 minus delta. It's the same expression. Okay, so so we're done with the proof that CountSketch is a subspace embedding, and using the connection to regression, we get input sparsity time and n z of a plus polynomial in d over epsilon. Okay. Any questions? Okay, great. Okay, so let's move on to the next thing I want to talk about, which is high precision regression, where we want a better dependence on epsilon. We want like a log 1 over epsilon dependence.
Good question.
Yeah.
Of those 3 methods there in the previous slide, which one of them is more numerically stable?
Numerically stable meaning like the condition number of something is good, or just if you implement it?
What numerical analysts would call forward or backward stability.
Forward or backward stability. I mean, so there are empirical results on this. Maybe Michael knows better than I do. But
I don't know about the CountSketch. I just don't know. But the other ones can be implemented stably.
Sorry, I didn't hear that.
I don't know about the CountSketch actually, but the other ones can be implemented stably.
yeah, I mean, CountSketch is extremely practical, and we have implementations on it where it works well. And it's a lot faster than Gaussian matrices, for example. But sometimes Gaussian matrices have other properties like smoothing out vectors, which is useful for other things like support vector machines, etc. Okay, high precision regression. So here is our goal again. We just want a 1 plus epsilon approximation to regression. And our algorithms run in poly d over epsilon time, but we would like poly d times log 1 over epsilon. So the idea is to first make our matrix A well conditioned. Okay, so the condition number for the purposes of this talk of A, kappa of A, is just the maximum value of the norm of AX divided by the minimum value of the norm of AX over all vectors X. Sorry, the supremum of the norm of AX over unit vectors X divided by the infimum of the norm of AX over unit vectors X. And lots of algorithms' time complexity depends on the condition number. So it'd be useful to have a generic technique for reducing the condition number. And so we're going to use sketching to reduce kappa of A to constant. Okay, so the idea is to let S be a 1 plus epsilon 0 subspace embedding for A. Epsilon 0 think of as a constant like 1/2. We first compute S times A, say using one of these CountSketch matrices. And then we compute a QR factorization of S times A. Okay, so we write S times A, let me just write it as Q times R inverse, where Q has orthonormal columns. Okay, and R inverse is just chosen to satisfy this equation. Now there are multiple different Qs you could choose, just choose one of them arbitrarily. Yeah?
Why have you got R inverse?
What's that?
Why isn't it just R?
Oh, I just want to define it like this for the purposes of the proof. I'm just calling it R inverse. Sorry, yeah, sorry. Yeah. Maybe I should call it R, but I'm going to use it, and I don't want to write inverses everywhere. So.
Oh, so this is a QR inverse factorization.
QR inverse factorization. Okay. Okay. So something to note here. I could have computed a QR factorization or QR inverse factorization of the original matrix A, but this would be slow, right? I mean, in general, this can take like n d squared time. Instead, what I did is I sketched the problem down to something small. So the number of rows of S is poly D. So this whole thing is just poly D by D. And now I compute my QR factorization of S times A in just poly D time, independent of n. And now what do? So my claim here is that if I look at the condition number of A times R, it's 1 plus epsilon 0 over 1 minus epsilon 0. Remember, epsilon 0 was this parameter, which I said is a half, say. In that case, this would be 3. I can set this to be any constant. I don't want to set it to be too small. If I set it really small, then I spend poly d over epsilon time here. So I wanted to set it to be a constant. So it's poly d time. The claim is that this holds. So just some perspective here. Like I compute like a change of basis in the sketch space, and I lift it up, use that same change of basis matrix, that d by d matrix, in the original space. So do people see why this should be true? Like what do we know about S? So why should this be well conditioned?
AR x is roughly equal to SARX, so, and the R cancels. Okay.
Yeah, perfect, right? Like so. Okay, so let's do what Ravi said. So for all unit vectors x, well, what do we know about the norm of SARX? Well, SAR, if I multiply both sides by r, it has orthonormal columns. So the norm of SARX is just 1 if I apply it to a unit vector. On the other hand, well, S is a subspace embedding, right? It's a subspace embedding, a 1 plus epsilon 0 approximate subspace embedding. So it's at least 1 minus epsilon 0 times the norm of ARX. This is for all vectors x. I can also do the other direction, right? I mean, again, the norm of SARX is 1, as before. And because it's a subspace embedding, it's at most the norm of ARX times 1 plus epsilon 0. Okay. But now I just take the ratio, right? The condition number of AR is just the ratio of the sup of this over the infinity, the infimum of the norms over all unit vectors x. And what do we get? Since this holds for all unit vectors x, it means the norm of ARX is at most 1 over 1 minus epsilon 0. And we also know that the norm of ARX, well, it's at least 1 over 1 plus epsilon 0. So when I do this division, I just get 1 plus epsilon 0 over 1 minus epsilon 0, right? Okay, so in n and z of A plus poly d time, we computed a matrix R, which gives a good preconditioner. Now what can we do? What can you do if your matrix is well conditioned? How can you solve least squares regression?
Invert normal.
What's that?
Use the normal.
You can use normal equations, but have you gained something by directly using normal equations?
You can use the explicit form. Invert.
So if you use the explicit form, that's the normal equations. So we want to avoid like nd squared time. Gradient descent, right? So gradient descent, typically the time for gradient descent is in terms of the condition number, but our condition number is very small now. So, okay. So, gradient descent, it also needs a good initial solution. Right? You have to start somewhere. Where are we going to start from? Well, we're going to start from a constant factor approximation. So, again, S is one of these 1 plus, say, 1/2 subspace embeddings. We compute SAR, SB. We compute SA, then SA times R. So this is n and z of A plus poly d time. We solve this in poly d time. There's no dependence on the actual epsilon. And we get our constant factor initial solution, x0. Okay, so we have our change of basis and constant factor solution. And now we just run a gradient descent algorithm, as you guys suggested. So let's do the update rule that the new iterate xm plus 1 is the old iterate xm plus A transpose R transpose times B minus AR xm. Okay, so B minus AR xm is what's left over, the residual in the mth iteration. And we're hitting it, we're looking at what's left over, and we're taking the inner product with the row span of R transpose A transpose, so the column span of AR, and we're moving a little bit in that direction. Okay?
Don't you need a step length?
This is my, no, so you'll see the proof. The whole proof will be on this slide. This is, the step length is just 1. Yeah.
Well, this is the same amount of work as a conjugate gradient method.
Well, the nice thing here is that the running time is going to depend on the condition number. But we've made the condition number small.
I mean, each step, the products with A and A transpose, the same work as a conjugate gradient method.
Yeah, so, okay, so let's look at the time complexity of this. So, what am I doing? I'm never actually computing this product, R transpose times A transpose.
No,
Yeah.
just the product on the vector.
Sure. Yeah, that's all I'm doing, right? So the important point to note here is I have xm, I compute xm times r, and I have rxm, that's a vector. I compute that times a. I subtract that from b, that's a vector. I compute that vector times A transpose, that vector times R transpose. I never have to compute the matrix-matrix products.
Oh, well, that's the same as a conjugate.
Yeah, sure. I'm just saying that, this will just give a very, the use of sketching here is for the purposes of making the condition number constant. Okay. If you don't have constant condition number, then are you going to get input sparsity time, n and z of a times log 1 over epsilon? So let's revisit the question at the end of the slide. Yeah. Okay. Okay, so let's just look at this quantity. Let's look at AR times the m plus first iterate, xm plus 1, minus the optimal solution, x star. Okay. Now, all I did on this right-hand side here is I plugged in, the definition of xm plus 1. This is the definition. Okay. So I claim the following equality holds. And this is, not so easy. Well, I mean, we should expand this just to see why this holds. So I claim that AR xm plus R transpose A transpose B minus AR xm minus x star is equal to AR minus AR R transpose A transpose AR xm minus x star. Okay, so here I have AR xm minus x star, and here I have AR xm minus x star, right? So what I really need to show that this holds is I need to show that AR times R transpose A transpose B minus AR xm is equal to this quantity, which is minus AR R transpose A transpose AR xm minus x star. Is that good, everyone? Okay. So I just have to show this equality. And both of these you have an AR R transpose A transpose times AR xm that occurs in both of these, right? So really you just have to show that AR R transpose A transpose B is equal to AR R transpose A transpose AR x star. Is that right? Did I get the signs right?
Yes. No.
Oh.
You just need a minus.
No.
Oh, sorry. That's right, right?
Yeah, it's okay.
That's right. Okay. Okay. So why is this true?
From the Dimensionality condition.
Exactly. From the normal equations, right? So this will follow if R transpose A transpose B is equal to R transpose A transpose AR x star, right? Because in both cases I'm multiplying by AR. So I'm just showing this is equal to this. These are exactly the normal equations, right? If I look at, solving the regression problem, ARX minus B, then I would get these normal equations, right? Okay, so that's why the second equation holds. Questions? Okay. Okay, so let's look at this expression, AR minus, AR, R transpose, A transpose, AR. Well, what's going on here? So this is, these matrices, this is like a matrix times its transpose times itself. So it's a matrix minus that matrix times its transpose times itself. So the left and right singular vectors, the U and the V transpose in the SVD, are the same. Is that clear to people? If you haven't, okay. So right. So what am I doing there? I have a matrix B. Let's just call B equals AR, and I'm looking at B minus B transpose B, right? And I can write B, it's always sort of useful to first write it in an SVD. So that's the singular value decomposition of B. And I can write B transpose as V sigma U transpose. And so if I look at B transpose B, B times B transpose, well, the V's are going to cancel because they're orthonormal. So I'll get U sigma squared U transpose, and then the U transpose cancels by the U when I multiply again, so I really just get U sigma cubed V transpose. That's good, everybody? Okay. And B is U sigma V transpose. So if I look at the difference, what I get is U sigma minus sigma cubed V transpose. Is that clear? Questions? Okay. So that's exactly what I have here. U sigma minus sigma cubed V transpose times xm minus x star. Questions? Okay. What do we know about all the entries of sigma minus sigma cubed?
1 plus or minus epsilon.
What's epsilon?
Isn't the condition number of AR very good?
Yeah, exactly. So, all of these entries are 1 plus or minus epsilon 0. Right? Because AR is well conditioned. I'm computing its SVD. What does it mean to be well conditioned? It means all the singular values are within 1 plus or minus epsilon 0 from each other. So I have these terms on the diagonal. They're all 1 plus or minus epsilon 0 in that range. And I'm subtracting off the cube of them entry-wise. So the difference on each entry is going to be order epsilon 0. Clear? Okay, and epsilon 0 is an arbitrarily small constant. I can set it to be whatever I want. Okay, so why don't we look at the norm of this quantity? Okay, so the norm of this quantity, well, I'm looking at the norm of this now. U is an orthonormal matrix, so it doesn't change the norm. I can just drop it. Sigma minus sigma cubed, so I get sigma minus sigma cubed V transpose xm minus x star. We said all the entries of sigma minus sigma cubed are order epsilon 0. So this is order epsilon 0. I can take this out. Order epsilon 0 times the norm of V transpose xm minus x star. Now I claim I can just plug back in U sigma into that expression because U sigma is well conditioned. And then when I plug back in U sigma, I just get AR there. Is that clear? So it's order epsilon 0 times the norm of AR xm minus x star. Right? So it's actually, you get an order epsilon 0 from this difference. I have a V transpose here. So I have to multiply back in U sigma. But U sigma, it only distorts norms by 1 plus epsilon 0. So I get order epsilon 0 times 1 plus epsilon 0, which is just order epsilon 0, times the norm of AR xm minus x star.
Sorry, why does U sigma only
Yeah, so the norm, so U sigma is almost like an orthonormal basis, but the singular values, instead of all being 1, they're between 1 plus or minus epsilon 0 because it's well conditioned. So it distorts things by at most that amount. Yeah.
Where did the AR come back?
Yeah, that was just that question. So we have a V transpose here. So we took this part out. we have a V transpose, and we have an AR here. So to go from here to here, I have to multiply in by U sigma, because U sigma V transpose is equal to AR, right? That's its SVD. Now what happens to a vector when I multiply it by U sigma? U sigma is almost well conditioned, right? Because we made sure that AR is well conditioned. So all the singular values of, in sigma, they're all 1 plus or minus epsilon 0. So I can put back in the U sigma, and that just multiplies this by 1 plus epsilon 0. And maybe I should write that. Is that not clear? Yeah.
Could we also just say you pull out I minus sigma squared?
Yeah, I'm sure there's a better way of writing this.
Like leave a factor of sigma, so it's sigma times V transpose. Pull out I minus sigma squared.
Yeah, I could leave sigma V transpose here and pull out I minus sigma squared. Yeah, that's a better way of doing it. And then I have to pull back in a U. And then U is orthonormal, so it preserves all the norms. Was that alternative argument? Was that clear? Any questions? Yeah, Ravi.
I mean, just another way of doing it is not doing all this stuff, right? The left-hand side is AR times that vector. AR singular is almost 1, so the length is almost preserved. And the right-hand side is epsilon times the length of the
yeah, so what we did is...
So xm plus m minus x star is the order epsilon times xm minus x star in length. This is what you're saying.
Yeah, ultimately I want to relate like what's happening in the mth plus first iteration to what's happening in the mth iteration.
Yeah, that just follows because of those lengths.
Yeah. Question, yeah.
But our original problem was to solve ax minus b minimum, so we have...
Exactly, so we're not done yet. Yeah. But what have we showed? We've showed some kind of progress, right? We've showed that the norm of AR xm plus 1 minus x star is at most like a small constant. I can make this like a half times the norm of AR times xm minus x star, the value in the previous iteration. Okay, so it's dropping. And how much does it drop? Like if if m is equal to log 1 over epsilon, then I can iterate this equality, and then the norm in the log 1 over epsilon iteration is at most the actual epsilon times the norm in the 0th iteration. The norm in the 0th iteration, well, we started off with a constant factor solution. So it's at most like, 3 times optimal or something. And now we get epsilon times 3 times optimal. So it's going to be order epsilon optimal. Because that's what's happening here. But let me just say what the last line is, which is going back to a question. What do we care about? We care about the norm, or say the squared norm of AR xm minus b, right? That's the regression problem. There's a minus b there. Well, what do we know? Well, the claim is I can write this squared norm as the norm of AR xm minus x star squared plus the norm of AR x star minus b squared. Why can I do that? You guys all know this. I just want to make sure people are following.
X star is a component of...
Yeah, so x star is the optimal solution. This is again the normal equations, right? So this is the optimal. This is the part inside of the subspace, and this is the optimal distance. Okay, so this is opt cost, and this is what we just bounded: AR xm minus x star squared, that norm. And so we just said that this thing, if we set m to be log 1 over epsilon, gives us order epsilon times the cost of our constant factor solution. So we get order epsilon opt for this term, and this term is opt. Overall, we get 1 plus order epsilon times opt. Is that clear to everybody?
So then why is the equality important in the last line?
Well, okay, in the last line, how are you going to get from, this is the objective you care about, and this is the bound that you have, inside of the subspace. So the idea is just, to move yourself inside the,
It's L2 squared, okay.
L2 squared, yeah. That's Pythagorean theorem. Yeah. It's like the part from B to the optimum, and then the part inside of the subspace. Okay, so we get a log 1 over epsilon dependence for regression. That's all I wanted to say about that. Yeah.
I think I missed something. So I thought X star was the solution for the AR regression problem, right? Not the AX minus B problem. X star is opt for what?
I can take AR. X star is just. I can take the optimal for AR. Yeah.
So I think I'm missing the last step, which is that you wanted to originally solve.
You have to plug R in.
You use RX star.
Oh,
RX star.
what AX?
Rx star for the for the A problem, right? Yeah.
Won't the condition number problem pop up there? Because you have to convert back from this x star to that x star, and that's solving the system Rx equals, x star. Let's say Rv equals x star. And will that problem occur there, where if that system is ill-conditioned, you could...
Sorry, this x star here, this is all with respect to AR, right?
Exactly.
So should that be x0? It's defined in the second line.
Oh, it's defined in the second line. Yeah. So x0 is. Oh, I see. Yeah, exactly. So that should be where x star is defined. Yeah. So x star is the x star is the minimizer for AR x minus b, and you're getting an x0 where the cost is at most a constant factor of that using x star.
But the original problem was solving AX minus B.
You first replace that problem with AR x minus b. So like if I'm going to compute a 1 plus epsilon approximation to AX minus b, if I look at a 1 plus epsilon approximation to this, what the cost here, it's the same as the cost here. Right? This is just a change of basis. So as I'm ranging over all x, I'm getting. So I first replace the original regression problem with the regression problem where A is replaced with AR. And now everything is done with respect to AR. So x star is with respect to AR. Yeah.
But if you care about the original solution, you might...
Yeah, so this is just so this is preserved. So approximation is preserved as well, right? Like if I get a 1 plus epsilon approximation to one, I get a 1 plus epsilon approximation to the other in objective function value. If you care about the actual solution vector x, then you have to map it back with R inverse x. But that's a different question, right? All I'm trying to do is preserve the regression cost solution. Yeah.
How did you get the bottom line?
Okay. So this is the, in general, like, it's just the normal equations, right? So, right. So
follow from the line before.
So let's look at AR x minus b for an arbitrary vector x, right? So I have this subspace AR here, right? And here is ARX, it's sitting somewhere here, right? For some particular x, right? Now I have my b over here, and its projection onto this space is given by ARX star. That's the optimal solution, right? So by the Pythagorean theorem, this squared cost is this squared cost plus this squared cost, right? This is just the Pythagorean theorem.
Oh, okay.
So that's all that is. Yeah.
Oh, thank you.
Sure. Is that clear? Okay. Yeah, question, Fred.
From a practical point of view, how would this, I don't know if you have had experience implementing this.
Yeah, we have implemented this.
How would that compare with, say, getting the matrix R, use that as a precondition or in something like LSQR or Mengues or that kind of stuff? How does that compare? Did you guys ever try?
I didn't. Yeah. So we have a KDD paper this year. You might want to check out. Well, we basically implemented many, sketching-based preconditioning methods, and but yeah, really the point here of sketching is just to reduce the condition number and then feed it into whatever algorithms that you want. Yeah. Question, Elias.
Can I ask a naive question?
Yeah.
So the second to last and the previous bullets, basically this analysis of gradient descents, you did it for pedagogical reasons, right? So like when you have a gradient descent with bound condition number, these things follow as a black box from standard. Just did it explicitly here for this particular setting.
That's right. This really is a gradient descent algorithm. Yeah, and this is really a step size in the gradient, like up to, if I put like a 1/2 squared norm, then this would exactly be like the coefficient would be 1. Otherwise, you should put a 2 here, but it doesn't change. Yeah. Yeah. Question, Fred. Yeah.
If we add a momentum by any chance here, would that improve on the dependence of epsilon 0? Or does it matter at all?
So you want to improve a log 1 over epsilon to something else, or?
Yeah, I wonder whether if we, instead of just simple gradient descent, we do, say, accelerated version of it. Would that help
in obtaining a better dependence on epsilon at the end?
No, epsilon is the same. The difference is in the dependence on condition number, which here is close to 1. So if you take a square root of condition number, you don't gain it.
Yeah. Or even like average condition number. They're all close to 1. Yeah, yeah. Question?
Do the last two bottom lines give you a real bottom line? What are you deducing from?
What am I deducing from all of this? Yeah. Okay. Okay. So let me just recap the algorithm. We have our matrix A. It's poorly conditioned. So what we did first is we found this matrix R, which gives us a good preconditioner. We did that in input sparsity plus poly d time, independent of epsilon. We also have our matrix A and our vector B, and we found a constant factor solution, independent of the actual epsilon in the same running time. Now we said, let's take those two quantities and let's run gradient descent. So this is a gradient descent algorithm. At the end of the day, if you output xm, where m is like log 1 over epsilon, then the claim is that the overall error, that you get a 1 plus epsilon approximation. Now why is that? Maybe I didn't emphasize it enough. Like on the second line here, this is relating the m plus first iteration to the mth iteration. So I can apply it again, and then I get order epsilon naught squared times AR xm minus 1. And I can keep applying it. And if I apply it log 1 over epsilon times, if this is like a half, I'll get 1/2 to the log 1 over epsilon, and it'll become epsilon. So that means that this norm is at most epsilon times the norm of AR x0 minus x star. And the norm of AR x0 minus x star, well, that's a constant factor solution to the original problem. So it'll be epsilon times, 2 times opt cost. Does that make sense? Or no, or no. Sorry, where did I lose you? Like so you agree that I can apply this log 1 over epsilon times?
Yeah, that's good.
And then at the end I get order epsilon, the actual epsilon, times the cost of using x0. Okay.
So it's monotonically decreasing.
And very quickly. Yeah. It's that's the point, that it's decreasing like a logarithmic number of iterations makes it get all the way down to epsilon. And that wouldn't have been possible without this condition number bound. Like we use the condition number multiple places in this proof. And to get that we use sketching.
So
yeah.
This analysis applies to any good preconditioner, right? Not just the one that you
exactly. Yeah. So you could have applied this to any good preconditioner. You do need a good initial solution, right? Because at the end you're going to get x0 minus x star. It has to be a good initial solution. And we use sketching for that as well. But if you had some other way of getting a good initial solution, you could have used that. Question.
You are first using sketch S to compute R, and then you're using some other sketch to compute this x naught.
Yeah, I mean, you can use the same one and then do a union bound. Yeah. Okay. Any other questions? Oh, yeah.
Just say what's the computational cost for each step up?
Yeah, what's the computational cost? What was the whole point of this? So we have log 1 over epsilon iterations, right? And what are we doing in each iteration? Well, we're doing this update rule. And we have some vector xm, and all we're doing is matrix vector products. We compute R xm. That takes order d time. Now we have a d-dimensional vector. We compute a times that. That takes n and z of a time. And now it's an n-dimensional vector. We subtract it from this vector b. That's order n time. And now it's an n-dimensional vector. We compute a transpose time that. That's n and z of a time. D-dimensional vector. Order d time to compute that. So it's n plus d plus n and z of a times log 1 over epsilon. Yeah. Any other questions? That's good. All right, good. So you can get log 1 over epsilon dependence for this problem. Let me just quickly move on to low rank approximation. I wanted to say something about this. Okay, so here's another very important problem in linear algebra, machine learning. You have an n by d matrix. Now think of both n and d as potentially being large. It's no longer tall and thin. And think of the n rows of A as being points in R to the d. You guys know all kinds of applications of this. So A could be a customer product matrix, and Aij might indicate how many times a customer purchased an item. In many settings, A is typically well approximated by a low rank matrix. It might just be high rank because of noise. And the goal is to find a low-rank matrix approximating A. Why would you want that? Well, instead of storing like ND parameters for A, you can store like the two factors of a low-rank approximation. Like if I write A as U times V, where I have rank K, then it's only like N plus D times K parameters. And so it makes it easy to store, and if I'm really removing noise, it can make it more interpretable. So the goal is to find this matrix A. And the natural way of doing this, the standard way of doing this is, as Ravi mentioned, is via the singular value decomposition. So I can write A in its singular value decomposition, U sigma V. And the best low rank approximation under many different notions of best is given by the so-called truncated SVD. So what is the truncated SVD? Well, I compute the SVD, U sigma and V, and then I just take the top K entries in sigma. Recall that they're non-decreasing as I move down. I take the top K, I leave them alone, and I zero out everything beyond that. So sigma K only has K non-zero entries, effectively selecting the K leftmost vectors of U and the K uppermost vectors of V, which are called the principal components, top K principal components, and I get some error matrix. Okay, this is the standard way of doing low rank approximation, but it takes SVD time. Okay, and we said SVD is slow. It can take like ND squared time, and we want much faster algorithms. The SVD is great. The solution you get, A sub K, via this truncated singular value decomposition, is the arg minimizer over all rank K matrices B, approximating A in Frobenius norm, but in fact in many other norms, any unitarily invariant norm. But as we said, it's expensive. Okay? So we want to use sketching to speed this up. Okay. So the goal instead is to relax the problem and to allow for outputting a rank K matrix A prime whose cost is at most 1 plus epsilon times the cost that you would get by using the SVD. Okay. One thing we showed is that you can do this using sketching in time, which is number of non-zero entries of your matrix A plus what's typically a low order term, n plus d times a polynomial in k over epsilon. Okay, so just some perspective on the bounds. So remember, SVD, it gives an exact solution, but it takes nd squared time. Even if your matrix is dense, like has nd non-zero entries, this still gives nd time versus nd squared time, so it's an improvement. And for sparse matrices, it really gives you an optimal running time, number of non-zero entries. And that is in fact optimal. If I have one very large entry of A and I don't find it, I don't read all the entries, then I'm going to be in trouble, because the first thing any good low rank approximation would do would be to try to fit that very large entry of A. Okay. So that's the claimed result. Let me just give you some intuition how this is shown. So the idea is to, again, thinking of A as its rows as being n points in R to the D. I've drawn them here. The first step in these algorithms is to compute S times A, where S is one of these wide fat matrices, these sketching matrices that we've been talking about. It has a small number of rows, roughly k over epsilon rows. Think of that. So when I compute S times A, what I'm doing is I'm taking k over epsilon random linear combinations of the rows of A. Right? Now I can look at the span, the row span of those k over epsilon linear combinations. That's a low dimensional subspace, which I've drawn as a line here, of R to the D. Right? The span of the rows of S times A. It's this low dimensional subspace I've drawn as a line. That's the first step in the algorithm. And the only remaining step is just to take your n points, these rows, and project them onto this low dimensional space, S times A. So to find the closest point in the space S times A. Now what have we gained by doing this? We still have n points, but now instead of living in R to the D, they live in this very low dimensional subspace, this k over epsilon dimensional subspace. Now if you remember the SVD, the time is like number of points times dimension squared time. We still have n points, but the dimension instead of being D, is now K over epsilon. Yeah, question.
What's S times A versus SA?
Oh, that's the same thing. Sorry. Yeah.
Thing.
Yeah.
Is one of them a matrix and one of them a subspace or something?
Yeah, sorry. So what I meant by this drawing, so I do compute S times A. Now S times A has a small number of rows, K over epsilon, and D columns. Now I can look at the span of those K over epsilon rows, any linear combination of those K over epsilon rows. And that's what I'm drawing with this line. It's a subspace of R to the D. Right? It's all the points inside of that space. And I'm taking each of my n original points, and I'm projecting them onto that span.
So this is the row space of S times A?
The row space of S times A. Yeah. Question?
So you wrote that K over epsilon is much less than n, but actually for this to make sense, it has to be much less than D as well, right?
Yeah, sorry. Well, so both n and d I'm thinking of as, yeah, as being large. It's much less than both n and d. Yeah. Questions? Okay, so you see, like, the point of this was to make SVD efficient. We reduced the dimension from D to K over epsilon. Now you might be asking a bunch of questions, you know, which matrices S work? You know, all the usual ones we've discussed work. I'll describe that. You might be asking, how do I project the points onto this space? How can I do that very quickly? Can I do that quickly in the time bounds that we want? And you might be asking, like, you know, what am I doing at all? Why does this even work? Why should I project them to this space and then solve for the best rank K space there? So these are the three questions that I hope to answer. Okay, first, what is the matrix S? All the usual matrices will work. So a matrix of ID normal random variables with roughly K over epsilon rows. This turns out to work. Or a fast Johnson-Lindenstrauss matrix. An example is this subsampled randomized Hadamard transform we saw with, again, roughly K over epsilon rows. That works. Or this CountSketch matrix works. But now you need a larger number of rows, which is like I've written as a polynomial in K over epsilon. Okay? The precise dependence is K squared plus K over epsilon, if you're interested. Okay. And remember, these were these sparse matrices. Okay, so let me just recap the algorithm and see where we are. The first step is to compute S times A. S is one of these CountSketch matrices, so I can compute this, you know, super fast input sparsity time. The next step is to project each of the n rows of A onto the space S times A. So it's not clear how to do that so quickly. Let me get back to that. And finally, once we have each of the points inside of this low-dimensional space, then now we said SVD is efficient because, you know, we have n points in K over epsilon dimensions, so we can solve it in n times poly K over epsilon time. That's the algorithm. The bottleneck is step 2, doing these projections. So how can we project each of the n rows of A onto S times A? Quickly. What is projection?
Least squares.
Yeah, projection is just least squares. And we saw all these fast algorithms for least squares, you know, earlier in this tutorial. So instead of actually computing the projection, why don't we approximate the projection? So it's a fast, there are fast algorithms for approximate regression. I can just write down what the regression problem looks like. It looks like the following form. The min over rank K matrices X of the squared norm of XSA minus A. Why does it look like this? Well, there's an argument that the row span of S times A contains a good solution. I'll get back to that in a moment. But let me just say why this implements what the algorithm is doing. Well, you're trying to project each of the rows of A onto the row span of S times A. So I look at the first row, and the first row of X gives me the corresponding coefficients, you know, for the projection onto the row span of S times A. Second row, etc. I'm minimizing the sum of squares of differences, so it minimizes the sum of squares for each row. It's giving me the projections. And the fact that X is rank K, well, I folded in the third step into the second step. Right? Because in the end, I need a rank K matrix here. Okay? And now there's a fast algorithm for this. So we said we don't know how to solve this exactly. But by using sketching techniques that we developed earlier in the tutorial, instead of solving this, what happens if I multiply on the right by another CountSketch matrix R and another CountSketch matrix R here? You can show that, you know, the cost is preserved. Okay, so additional sketching on the right preserves the cost of this objective function, where the number of columns in this matrix R doesn't even depend on D. It's now poly k over epsilon. So it's additional sketching. If you put it all together, so I'm skipping the details of this step, then you get overall n and z of a plus n plus d poly k over epsilon time. Yeah, quite, okay. Yeah. So really this is just using techniques earlier in the talk based on least squares regression. The main question here, dangling question is, why even project the rows onto the row span of S times A? Why should that be any good? So here's a sort of a cute argument that reduces low-rank approximation to regression in a certain sense. So let's look at a hypothetical regression problem. The min over matrices X of the Frobenius norm of AKX minus A. Okay, AK is the best rank K approximation to A, given by the SVD. So what is the minimizer X here? Identity, right? Okay, so I just set up some problem. Let's look at a sketch version of this problem. Okay, now I don't have time to define what's called an affine embedding, but what you can think of an affine embedding as is it's a subspace embedding, but for a shifted subspace by some fixed amount. So I'm going to look at the column span of AK, but it's going to be shifted by this matrix A. And what you can show is that there's a generalization of a subspace embedding called an affine embedding, so that the norm of SAKX minus SA is 1 plus or minus epsilon, the norm of AKX minus A for all matrices X. Okay, so without the A here, this would just be a subspace embedding property, right? Because AK has rank K, and the size of a sketch to preserve a rank K space is poly K over epsilon. Okay. Are you guys with me here, or some confusion here? Okay. So I didn't have time to define this affine embedding, but this is a property that you get. It has a small number of rows, and it preserves all these costs. Okay. What is the solution to this problem? So I've replaced AK with SAK and A with SA. I get this new regression problem. It's a sketch problem. Well, we know how to write down a closed form solution for regression, right? The solution, the minimizer X, is SAK inverse times SA, a pseudo inverse. Remember we looked at pseudo inverses. We said the solution to a regression problem is this pseudo inverse times this. So that's the solution. Okay, what was the point of all this, right? We don't know A sub k. So why did I do this? So what's one nice property about this matrix? So it's rank K, right? And what else can I say about this matrix? What is it?
It's the identity.
It's not the identity, right? Because it's SAK pseudo inverse times SA. Right? This is just SA. This is a rank K matrix. It's not the identity. But what's that? Yeah, more pen rows, the pseudo inverse will give you a minimum norm solution. But where does this matrix live? Like, where do its rows live? What subspace do the rows live in? Yeah, I think someone said it.
SA.
SA, right? This is a matrix which has rank K, and it lives inside the row span of SA. And moreover, by this claim here that I didn't prove, we know that any solution I get here gives me a 1 plus or minus epsilon approximation if I plug it back into the original problem. So if I take this solution X and plug it back into this original problem, then I get AK times this solution, SAK inverse SA, minus A is less than 1 plus epsilon times the optimal solution cost. Right? All I did is I took this solution to the sketch regression and plugged it back into the original hypothetical regression problem. So what does that mean? Like, look at this equation. It says, here's a rank K matrix. It's inside of the row span of SA, and it's giving me a 1 plus epsilon approximation. So it does make sense to take my rows of A and project them onto the space S times A, because I know inside of there's a good 1 plus epsilon approximation. I mean, maybe I'm not going to find this one, and I'm likely not going to. But what am I going to do after I project my rows onto that space? I'm going to do the SVD. And that gives me the best rank K approximation inside of that space. So it's at least as good as this one. Right? Is the picture clear? Like, sorry, almost done. Yeah. Like, we have this space SA. We took our n points and we projected them onto here. And now they're all inside of here. And now we're trying to find like a k-dimensional subspace inside of here, which is good. And we know there exists one that's good, this one. But what we did is we computed the SVD of these points inside of here and took the best rank K solution. So that's even better. Because everyone has to pay this cost of moving to S times A. And by Pythagorean theorem, now I just pay this cost. And I'm paying something even smaller by using the SVD than what I might get by this particular subspace. Okay, so just to conclude, it's a rank K matrix in the row span of S times A, and Pythagoras says projecting the points onto S times A and finding the best rank K solution inside of SA gives a rank K matrix at least as good as this particular one that we found. So that's why the algorithm works. That's why it's a good thing to project onto the row span of S times A. Any questions about low rank approximation? It's clear? Yeah, question.
How do you get this fine embedding?
Yeah, so I didn't prove this for time constraints, but it's just a natural generalization of a subspace embedding, and you can show that CountSketch also satisfies this property. Yeah. Any other questions? Yeah, Michael.
A is certainly a tall matrix.
Here A can be arbitrary dimensions. It doesn't need to be, yeah. So N and D could both be large. Yeah.
I was going to say, is SA tall? Or?
It's arbitrary. N and D can both be large, yeah. Yeah. Yeah, question, yeah. Yeah, good question. So I didn't say what it is. For CountSketch, you can get something with k squared plus k over epsilon rows.
And that's what actually appears in the running time.
Yeah, so this is the number of rows, and then when I say poly k over epsilon, this appears in that polynomial, that running time. Yeah.
Okay, because there is nothing else.
Yeah, that's right.
Have you made an effort to optimize that? This additive poly k over epsilon term? Like, is there an interest in that, or is it like small enough so it doesn't matter?
I would say both. Okay. Yeah, it's unclear what you set K to be in practice, but there is definitely, using some of these trade-offs that I said, instead of one non-zero entry per column, if you use a larger number, you can reduce this K squared to something smaller. Yeah. Any other questions? Yeah.
What is the running time of that projection?
So the overall running time of this algorithm is number of non-zero entries of A plus n plus d poly k over epsilon. Yeah. The approximate projection step inside of the algorithm is also in this amount of time. Yeah.
So where does the plus d come from? The n times poly k was clear. D times poly k?
Where is the d? Let me go back to the algorithm. Okay, so yeah, this is n times poly k. This is n and z of a. Projecting the rows onto this Yeah, no, actually, this algorithm is just n times poly k over epsilon. So yeah, that's right. Yeah. Yeah. So when I compute on the right by a CountSketch matrix here, the time can be done in n and z of a time. It doesn't go into the there's no d here. Yeah. Any other questions? Okay. Let me just wrap up in like a few minutes. I just want to mention, to advertise sketching, many of the other applications that it's useful for. So it's useful for these CUR decompositions, which is what Ravi talked about, where you want specific kinds of low-rank approximations, where your factors C contains an actual subset of a small number of columns of A, and R is a small number of rows of A, and U is an arbitrary rank K matrix. These are very useful low-rank approximations because, for example, if your columns of A were sparse, then your factorization would also be sparse, your low-rank factorization. So you can get fast algorithms with sketching for that. There are also many robust variants of low-rank approximation. So instead of minimizing the sum of squares of differences, there's a lot of recent work trying to minimize the sum of pth powers of differences. A lot of these problems are NP hard, but you can get approximation algorithms. And these could be much better in the sense, if p is 1, these could give you much more robust solutions than Frobenius norm. There are kernel problems where you have points that are not linearly separable, but you can lift them to a space where they become linearly separable. And there are sketching-based algorithms to do this very quickly. Rasmus Peg has a nice paper on this. Clustering, k-means clustering, you can write this as a constrained version of low-rank approximation, and you can get very fast algorithms for k-means clustering based on fast algorithms for low-rank approximation. A lot of these sketching-based algorithms, what they do is they compress the input matrix to something much smaller. And so naturally, they're useful for low communication distributed protocols, where the matrix is distributed across multiple servers. Everyone can compute a sketch of their matrix and communicate this sketch to each other, which is much less communication intensive. Streaming models, you often have like very limited devices like routers on a network which are processing high-speed data. They want to use, if you use a sketch of your input matrix, then you can use a much smaller amount of memory than storing the whole matrix. A lot of these algorithms generalize to tensors, so you can do things like tensor low-rank approximation. Find outer product of 3 vectors. As Ravi mentioned, that would be the rank 1 version, and the sum of such outer products, sum of k of them, would be the rank k version. There are algorithms for that. Weighted low-rank approximation. In Frobenius norm low-rank approximation, we're trying to find a factorization, a rank k matrix, which minimizes sum of squares of differences. But maybe not all entries are created equally. Like maybe some entries we want to weight more than other entries. And so you could have a weight matrix which multiplies every entry of the difference. You can get algorithms for that. Structure preserving low rank approximation. Maybe your input matrix A is positive semi-definite. Then you might want your factorization to also be positive semi-definite. I mean, you're trying to approximate the original matrix. So you might want your factors to look like U transpose. And there are algorithms for that. Regularized versions of these problems. Maybe on this contour, all the solutions have the same regression cost. But maybe I'm only interested in solution vectors X which have unit L2 norm, or at most unit L2 norm. Or maybe at most unit L1 norm. This is the difference between ridge regression and lasso. And there are algorithms for that based on sketching. Okay, so that's it. This is just a summary. So thanks.
Any further questions? If not, let's start the evaluation and go for